Excuse me. All right, so for these notes, we're going to go over intermolecular forces. Intermolecular forces are extremely important for AP chemistry, and we'll revisit them then. But I want to give you the kind of basic idea. So the idea behind this is intermolecular forces stands for the forces in between molecules. So if you have separate molecules, how do they interact with each other? And the essential idea here is that they all interact with each other and they are all attracted to each other in some way, shape, or form based on electrostatic forces. So electrostatic forces are this idea of positive and negative charges attracting each other. It's all based off of a concept called the dipole. A dipole is a pretty fancy way of just saying that molecules have one side that's more positive and one that's more negative. So actually, if we go back to the polar versus nonpolar notes, all polar molecules have a dipole. And a dipole is just representing that idea. It has two poles, dipole. So for example, hydrogen chloride has a dipole. We usually draw these with these arrows with a plus sign on them. The plus sign represents the positive side and the arrow represents where the electrons are kind of congregating. It's also known as a dipole moment, but it's the same thing. So water also has a dipole. And they all do. So again, it's that idea of positive end, negative end. Now, all molecules have dipoles to some extent. Some are just not really permanent. Depending on what type of molecule you're dealing with, it's going to have different kinds of interactions with itself. So one example of that is an ionic bond. This is not officially an intermolecular force, but I like to think of it this way. So an ionic compound is not a molecule. It is two ions that are charged and attracted to each other because of electrostatic forces. So in that case, it's like an extreme dipole moment where, for example, you have sodium that's a +1 and chlorine that's a -2. Technically, when they're kind of next to each other, they can kind of trade that electron back and forth. It's just that the vast majority of the time, the electrons are going to be spending the vast majority of their time with chlorines. So much so that if they separate, the chlorine takes the electron. This is like very, very big. Okay. For covalent molecules, the electrons are shared a lot more evenly, but again, sometimes one has more than the other. So a typical type, one of the types of intermolecular forces, there's really only 3 types that we're going to work on for this, is dipole-dipole. So essentially what this means is that the two different sides of a polar molecule are attracted to each other. So let's think of a good example for that. Let me think of one here real quick. We'll be going. Let's do hydrogen fluoride. That's lovely. Oh dear, quite a storm brewing outside. Okay, so hydrogen fluoride has a slightly negative and a slightly positive end. So intermolecular forces are when you have more than one of the same molecule. Intra is a whole other thing, but inter. So what if you have a second hydrogen fluoride? Well, what will happen is this hydrogen fluoride's partially positive side is going to have an electrostatic interaction with this. Let me draw that in a different color. We'll use the purple. I think the purple is pretty good for this. It's not much different. Okay, it's going to have a little bit of an attractive electrostatic force between the negative side of the fluorine. So this is that dipole-dipole intermolecular force. So that's the attraction, the electrostatic attraction represented right there. Maybe I'll switch to a different color for the next one. I'll try like this, maybe this orange. Okay, it's not a bond. It's just a temporary interaction. So this is an example in a more three-dimensional way of this showing how there's these attractive forces in between and some repellent forces as well that push each other away and attract each other. So these are going to make a really big difference when you're talking about a liquid or a solid or a gas, like how much energy does it take to pull them apart, or how closely knit and how much do they hold on to each other? Okay. There's a subset of dipole-dipole that's called the hydrogen bond. It is not a bond. It is not a bond. I know it says hydrogen. It's very confusing, but it's actually not a bond. A hydrogen bond is when you have a hydrogen that is bonded to one of these three extremely electronegative elements, and they attract each other. So fluorine actually is one of them. Let's switch this to chlorine. Sorry, y'all. I didn't want to confuse you, but now I probably have. Okay, we'll make that chlorine. Sorry, that should say chlorine. Okay, if you have a hydrogen that's attracted to one of these, it's going to make hydrogen bonds. So let's do a quick example of one of those. Let's do, water is the classic example, but maybe we'll do something a little different. Let's do nitrogen trihydride. Okay, so there's a nitrogen trihydride. The nitrogen is very, has a really high electron affinity. There's another word for it, which is electronegative. It's the exact same principle. Anyway, it attracts a whole bunch of electrons. And this other side is going to be kind of positive. So if there's a lot of this, this is ammonia, actually. If there's a whole bunch of ammonia around, then you might see something like this. This nitrogen is going to be attracted. Oops, that's the positive. The other one's the negative. Sorry. Red means negative, blue means positive, you know. Okay, there's going to be an attraction between the nitrogen and the hydrogens, like that, right? So this side of the molecule, the positive end, is going to be attracted to the negative end of this one. Now, what's really special here is that this nitrogen is super, has a lot of electron affinity. It really wants these electrons. But so does this other nitrogen it's actually bonded to. So this hydrogen is sandwiched in between two very electronegative molecule, or two very electronegative, or two atoms with very high electron affinity. And so this creates an exceptionally strong dipole. This side of the molecule is way more positive than normal. This side is way more negative than normal. And so that attraction is really, really strong. This is the reason water is like the classic example of this, because because the bent shape of water creates this extreme dipole and creates very strong hydrogen bonds, which is why water can absorb so much heat before it evaporates, or takes a lot of heat to make it before it takes a lot of heat to make it boil, that kind of thing. And a lot of other cool properties of water come from this fact. Okay, so hydrogen bonding is very specific. It has to be a hydrogen bonded to something electronegative, interacting with something electronegative. So it has to be sandwiched between any of these combinations. So if you had like if you threw a water into here, it would also cause hydrogen bonding. I can actually draw that in as well. There's water. Water is very, very negative on this side, very positive on this side, not fully charged, but close. So this side, there could also be a hydrogen bond there. And in fact, this hydrogen bond would be stronger than this hydrogen bond because the oxygen has a higher electron affinity than nitrogen, right? Because of the periodic trend. So the oxygen is going to be, the water is going to be even more polar, even more negative on this side, even more positive here than even in this case. Also because that angle is so bent. Okay, so there's hydrogen bonding. The last one is electron dispersion, which is also known as van der Waals interactions or London dispersion interactions. This is the case. Every single molecule has these. They all do. Every single atom, every single molecule, this will happen. maybe not for, no, even for hydrogen, because there's no monatomic hydrogen, it's always diatomic. These other ones, it just depends on the structure of the molecule. Does it have a dipole, and is it an extreme dipole like with hydrogen bonds? Everything has electron dispersion forces. And this is what's called an induced dipole. So a polar molecule always has a dipole, has a permanent dipole. So this is an example of a helium. So generally speaking, a helium just has 2 electrons, and those electrons are going to just create a very symmetrical, sort of very non-polar electron configuration. There's not really a dipole here. But just based on pure random chance, at some point, the electrons are going to be spending more time on one side than the other. So that's what's being shown here. In this case, the electron's density is a little bit higher over here and a little bit lower here. And what that will do, because this side is slightly more positive, it's going to attract the electrons over to this side a little bit more. And now both of these have a very temporary, very, very, very short-lived induced dipole. And that's what creates electron dispersion forces. The more electrons that there are, the more likely this is to happen and the stronger it is. This is the force that holds coconut oil together. So coconut oil is a solid at room temperature because coconut oil has huge, huge, huge molecules. And the way that they stick together, they just kind of stick together, and that's what holds it together. There's not really any other forces holding oil together. So it can be a very strong force if there's enough electrons. There's just, there has to be thousands and thousands of electrons for that to be true. The shape of the molecule also makes a difference as well. Okay, the reason that we care about this, well, there's a lot of reasons. One of the main ones is this helps determine boiling points and melting points and freezing points. So the more forces that there are holding individual molecules together, that's going to increase the boiling point. So this is the reason why water boils at what, like 100 degrees Celsius, but ethanol or like rubbing alcohol evaporates if you just put it on your hand, because it boils at like maybe 70 degrees Celsius, quite a bit lower. And that's all based on their intermolecular forces and these properties that determine that. So if you know the boiling points of 2 different substances, you can guess at the differences in their structures and their different intermolecular forces. And if you know if you know what the structures are, you can actually guess which one has higher and lower boiling points, even if you can't necessarily like come up with a number. Generally speaking, this is the rule. Ionic bonds are the strongest, hydrogen bonds, dipole, then electron dispersion. So that's why they're in that order. Okay, let's take a look at some examples. There's a lot of pages to go through. So this is number 6, page 16. I'm going to say I would not worry about this section for right now. Maybe I'll talk about that if you want me to, but I can kind of go through a lot of this. This one, you just need to check out if you have thousands of molecules of each, what's holding them together. Oh, some of this is good. So for NH3, we actually just did that one. That's ammonia. We'll pick out a whole bunch of these. Ammonia has London dispersion forces. They all do. It also has dipole-dipole. It's a nonpolar molecule. It's a polar molecule. And it also has hydrogen. It does not have ionic bonds. It does have polar covalent bonds, though, which is, we didn't really talk about that, so don't worry about it. I wouldn't worry about it. Yeah, I would ignore that. Number 2, K2S. Now, this is a funky one. So K2S is really ionic. So I'm going to say it has ionic bonds. And so maybe we'll just throw this in. I guess it definitely doesn't have hydrogen bonding. I don't think it really has any of these others. I wouldn't really, once it's ionic, I wouldn't really worry. Intermolecular forces are no longer really relevant anymore. I don't think. Maybe London. I've never thought about it that way, so I wouldn't. Let's not worry about that. So ionic is another option. Let's do that. HCl definitely has London. Definitely has dipole. but actually does not have hydrogen because hydrogen bonding requires a hydrogen bonded to a nitrogen, oxygen, or fluorine. So that's no good. Fluorine is a nonpolar molecule. So it only has London dispersion forces because F2, right? You may have to draw out your models, right? NH3 is this one. Yeah, it might help to draw a quick Lewis model. Let's skip around a little bit. Let's go. Yeah, that one's kind of boring. Ooh, NO, that one's a fun one. NO has a nitrogen and an oxygen, so it's definitely going to have a London dispersion and dipole, but no hydrogen bonding because there's no hydrogen. Let's see. I don't really see any other ion. Oh, here's another ionic one. So that one's kind of stupid. Just ionic. Yeah. How about CH4? CH4 has London dispersion. We can draw out CH4 real quick. However you want to draw it, it's all good. That looks nonpolar to me. Because it's nonpolar, it does not have dipole-dipole forces because there's no dipoles, and it won't have hydrogen bonding either. Technically, it also has, if you're curious, it has nonpolar covalent bonds. HCl has polar covalent. F2 has nonpolar covalent. You might be able to figure out the trend. NaCl is ionic. Anyway, NO has polar covalent, no nonpolar covalent. Anyway, not important. Okay, so hopefully that makes a little bit of sense. Let's take a look at the next worksheet and we'll see what it has. Okay, what's the strongest intermolecular force present for each? So we only need to write down one. I saw acetone. Let's just do that one real quick because that's fun. Acetone, we're going to have to draw the Lewis model. It's that. So this is definitely polar. Now it's going to, because it's polar, it's going to have dipole-dipole. But the question is, does it have hydrogen bonding? Remembering our definition of hydrogen bonding, we have to have hydrogen atoms that are bonded to oxygen, nitrogen, or fluorine, which this doesn't have. Now, these hydrogens are going to interact with the oxygens of other acetone molecules, but it's not hydrogen bonding. So it's actually just dipole-dipole. So in this case, the dipole is this. That's the positive end. And that's the other one's the negative. Excuse me. Yeah. Okay. And acetone, also we kind of know this because water, it boils at a much, much lower temperature. Like it evaporates very quickly compared to water. So it makes sense that it doesn't have as strong of intermolecular forces as water. Water has hydrogen bonding, which is stronger, which is why it evaporates at a higher temperature. It takes more energy to break those intermolecular forces. Oh, I'm going to show you benzene real quick because this is my favorite molecule. I love benzene. Benzene is actually a circle, which you might not know unless you. It's also known as cyclohexene or cyclohexene. Yeah. Oops, I did that. Oop, oop. One. Oh dear, I think I misdrew it. It's my favorite molecule too. How could I misdraw it? Okay, something like that. There's 6 in a circle. This is actually nonpolar. There's nothing to that. So this one is going to be dispersion. London dispersion, van der Waals, electron dispersion, whatever you want to call it. What else we got? Anything else here that's particularly fun? No, we've done a lot of those already. All right, let's try the next page, see what we come across. Oh, now this is cool. This is a great table because it has everything. So molecular attraction, that's going to be your IMF. So let's pick out one of these. I like silicon dioxide. Bond type, I would say, is the thing you don't have to do. The electron dot structure here. Oops, there's no, I'm wrong. Sorry. The oxygens are the ones that have it. These are going to be considered, they're going to be considered not, are they polar bonds? They're probably polar. They're considered polar covalent bonds. You don't have to know how to do it. Don't worry about it. Because I haven't taught you about this at all. Because there's the electron affinity is not the same between these two molecules. So they're a covalent bond that are polar. Don't worry about that. The shape is linear, right? Because it's a straight line. The polarity is non-polar. And so the IMFs, therefore, are just dispersion. Okay, so that's what you can write. Let's see. HI. HI is fun. Yeah, why not? It's easy. Oops. That goes there. It's also a polar covalent bond, but we don't worry about that. This one's also linear. That's the shape, the molecularity. The polarity, it is polar, and it's going to have dipole-dipole. And it's also going to have dispersion because all molecules have dispersion. All atoms have dispersion. Okay, so you can kind of get the idea there. So this is a really great summary of everything we've learned, except for you can just skip that because don't worry about it. Definitely AP, but not right now. This is page 19. Predicting the shape, that's fun. Listing all the IMFs, also very fun. We've already kind of covered some of those. These ones is what force they have, and then their relative strength. So like 1, 2, 3, that kind of thing. And then page 20, everything that has hydrogen bonds, you'd circle, and you'd rank these from the strongest to least weakest intermolecular forces, and then these ones from the weakest to strongest, weakest to strongest intermolecular forces for all those. Okay, so those are fun. Definitely please give those a try. It'll make your life in AP chemistry a lot easier if you know something about those. You know, for this year, it's not required, but why not? Give it a try. All right, let me know if you have questions. It's cool stuff. Yay. Bye, guys.